optimization question. We want to find the value x for which this curve is closest to this point. And so in this case, right, we need to look at this word closest. This is going to be the biggest help for what we're trying to do here. When I say closest, that means I want to minimize distance. So that's the optimization that we're going for here. We're trying to find the minimum distance. That's what we mean by closest. Okay, so if you're interested in distance, well then it really helps to pull out our distance formula, right? And this will be given to us on the formula sheet. It looks like the difference in the x points, the x values of our point, and then the difference in the y value of our point. And then again, there's a nice picture that goes with this in the Pythagorean Theorem sort of deal. So if you have the point x1, y1, and the point over here, x2, y2, and again, you're interested in finding the distance between these things, then you kind of make a nice right triangle here. And then you want to know, okay, again, I'm trying to find d, and now you kind of see how the Pythagorean theorem comes into this, but we have to know what is the length of this. Well, you start at x1 and you move over to x2, and the question is, how many steps did you take? Well, that's going to be x2 minus x1. And it really helps to put some values to this. So, right, if you had x1 is equal to 1 and x2 is equal to 5, for instance, then, okay, if I want to get from 1 to 5, I would take 4 steps. Well, that's 5 minus 1. Likewise, if you had, right, you want to know this length right here, this is going to be y2 minus y1. And so this is where this distance formula comes from. Now here there's a lot of variables, x2, x1, y2, y1, and so we need to kind of restrict this down a little bit, right? Ideally we're doing single variable calculus, so hopefully I get something with just x's in it. So okay, maybe first of all, it looks like one of our points is fixed, right? So I have a point here. I'm going to go ahead and call this x1, y1. So, okay, this would be x2 minus 16 squared plus y2 minus, well, a negative, so plus 1/2 squared, all under my square root. Okay, so that point is fixed, and then the other point, right, it's not just anywhere in space or in the plane or anything like this, right? It's on this curve. Right, so we know that the x and the y are kind of related to each other. So I'm just going to rename x2 as good old x. So x is a point on this curve. And then if y2 is a point on this curve as well, then I know y is going to be equal to x squared minus 1. So I can go ahead and substitute that in. And now I have a distance formula that only relies on one variable, right? It only relies on x. So in fact, we could call this d of x, right? The distance that only relies on x. And so now that we have this good setup, we can go ahead and do the optimization, right? We're trying to find the minimum distance. I guess one thing that I would like to do that will kind of benefit us later on is that I want to first of all see that the distance is always positive, which makes sense, right? So the distance between 2 points is always going to be a positive number. We can see that there's squaring, and then you add to more squaring, and then you take the square root. The only time that this may not be positive is if actually they're right on top of each other, right? If this point happened to be on this curve, right? If I drew this curve right here, and that point 16 comma negative 1/2 actually lied on this curve, then the distance would be equal to 0. It's never going to be negative, but it's either going to be positive or it's going to be 0 if they lie, on each other. So let's go ahead and see, does this point lie on this curve? And the way that we do that, well, we plug it in and see if it satisfies this equation. So I'm going to do negative 1/2, that's our y value, is equal to, let's see, x squared, so 16 squared minus 1. Right, so there's our x and our y value. We plug that in and we can see that, okay, 16 squared, that's I think that's like 256 or something like that. 256 minus 1, that's going to be 255. Does that equal negative 1/2? Absolutely not. So the distance is always going to be positive. And again, this may not be useful quite yet, but the claim is it'll be very useful once we take the derivative and start analyzing this thing. So again, the point does not lie on the curve. Otherwise, the minimum value, the closest point would, it would just be on the curve, right? Okay, so it's off the curve, and so the distance is strictly positive. All right, so I've put it off long enough. Again, in order to figure out minimums and maximums, right, we need to take the derivative. We're looking for critical points here. So let's go ahead and take the derivative. In fact, I got one more step of simplification that I want to do before we get to that. And let's just write this as x minus 16 squared plus x squared minus a half squared, all under my square root. All right, now let's go ahead and take the derivative, and we're going to need a little bit of room for this. So this is a fairly complicated function. Right, so okay, the first thing that I notice is that there's a big square root happening here. Right, so that's the same thing as being raised to the 1/2 power. So when I take the derivative, the 1/2 is going to come down. I'm going to leave the inside alone, and then I'm going to reduce my power by 1. So that's going to go to the negative 1/2. All right, so let's go ahead and write in our inside here. All right. That's the derivative of the outside, leaving the inside alone. And there's one more important part, right? According to the chain rule, I need to multiply by the derivative of the inside. So now I'm looking only at the inside here. And I need to multiply by the derivative of this. Well, this is a complicated inside, so I'm going to do some parentheses here. So if I multiply by the derivative of, let's see, x minus 16 squared, that's going to be 2 times x minus 16. And now how about the other one? Let's see, the 2 would come down, reduce my power by 1. And so that's going to be raised to the first power. But actually there's something even, right, this isn't just x, it's x squared. So actually this has another chain rule going on here. So I need to multiply by the derivative of its inside. And its inside is 2x. All right. Now let's go ahead and do a little bit of simplification to look at this thing. So, okay, when I have raised to the negative 1/2 power, that's going to go ahead and push that into the denominator here. And this looks like the distance function right here. So, okay, this is going to be x plus 6 squared times x squared minus a half squared, because again, I left the inside alone. And then multiplied by, and let's go ahead and try to simplify this as much as possible. So this is 2x minus 32. Plus, okay, so here is 2 and another 2x, so that's going to be 4x that I'm multiplying by the insides here. So 4x times x squared, so that's going to be 4x cubed. And 4x times negative a half, that's going to be negative 2x. So actually, there's a little bit of cancellation, right? So we have the 2x and the negative 2x. That perfectly goes away. And if you'd like to, right, this is the same thing as multiplying by this thing over 1, so we could, multiply these fractions together. And so, okay, maybe one more step here. This is 4x cubed minus 32 divided by 2. Okay, let me do the simplification here. The simplification, the 2 is going to cancel out, and so I'm going to have 2 minus 16. Okay. That way this will be my final line for my complicated derivative. All right, so there is my derivative, and then the question is, where is this 0 or where is it undefined, right? I'm trying to find critical points. And so, okay, the easiest one is certainly if it's equal to 0. So if it's equal to 0, and I'm just going to write the square root of stuff down there, right? Well, the first thing I'm going to do is say, well, I don't like fractions. I'm going to go ahead and multiply by this denominator, right? If I go ahead and basically cross multiply, you think about, right? Or multiply by the square root of the quantity x plus 6 squared plus the quantity x squared minus a half squared, right? So if I go ahead and multiply that on both sides, well, 0 times anything is nicely 0. So that gets rid of all of this complicated stuff. Now we can go ahead and rearrange. So I'm going to get 16 is equal to 2x cubed. In fact, we could go ahead and divide by 2 at this line as well. So I'm going to get 8. And then the cube root of 8 is going to be 2. So x equals 2 is a critical point. Now, the question is What about when it's undefined? So we get critical points where either the derivative is 0 or where it is undefined. And so what it would take for it to be undefined, right, is certainly if you were to divide by 0. So if this was equal to 0, then we would get another critical point that we'd have to consider. Or if this was less than 0, right? Because of the fact that we have a square root here. So if it was less than 0, well, because we have a square root, that would also be undefined. That would not be a real number. Well, this is where I wanted to remind us, right, that this distance right here, so again, that square root with all that stuff, that's our distance. Distance is never negative, right? So you're never plugging a negative into the square root. You have lots of stuff squared here being added together. And the only case it's equal to 0, right, if the distance is equal to 0, that would mean that this point would actually have to be on the curve. So, is there any way that you can make this equal to 0? No, because the point's not on the curve. So this doesn't happen. And likewise, there's no way to make that negative. So that's to say that our only critical point is when x is equal to 2 here. Now, again, our goal was to figure out the x value, right, where this is closest to the point. I have only shown that I found a critical point. And remember, critical points fall into one of 3 categories. They're either minimums, maximums, or they're just boring critical points, right? And they don't actually relate to a minimum or a maximum at all. And so if you were to, imagine you're on an exam right now, if you were to just stop right here, you would not receive full credit, right? On maybe like a 10-point problem or something like this, I would probably grade this at around a 7. Yeah, around 7 points or so. And people could argue, they say maybe 6, maybe 8, stuff like this, depending on the instructor. But yeah, around the neighborhood of 7, right? You need to show that this thing actually minimizes distance. And so that's where we get this nice little number line, right? So we want to show that this actually minimizes distance at x equals 2. And so we draw the number line here, and remember we're plotting information about the derivative to try to show that it's a minimum. Now if all is going well, what I would like to see is that we have a negative over here and a positive over here. That means that our function would be decreasing, then our function would be increasing, right? Negative derivative, decreasing, positive derivative, increasing. So that means that 2 would be a minimum. That's what I'm hoping for. In order to check and see, does this really happen, right, I need to go ahead and choose some test points. So maybe I choose the test point like 0 and 3. So 0 and 3, and I plug those into my derivative. So okay, let's go back up here. Here was my last version of my derivative. Let's go ahead and plug in 0, for instance. So d prime of 0, this is going to be equal to, okay, the numerator is just going to be negative 16. And then in the denominator, we get the square root of, well, let's see, 0 plus 6 squared, that's going to be 36, plus 0 minus a half squared, that's going to be, well, a half squared is a fourth. So I have a negative divided by a positive. So when you have a negative divided by a positive, yes, you get out negative. So this one is true. How about when I plug in 3? So d prime of 3. And I go over here, again, I look at the numerator. So 3 cubed, that'd be 27 times 2, that's going to be 54. So that's going to be 54 minus 16. And again, the big thing here is that that's positive. How about in the denominator? So I would have the square root of, let's see, 3 plus 6 would be 9 squared, that's 81. And let's see, 3 squared would be 9 minus a half. So I'm just going to say 9 minus a half, I'm going to do 8.5 squared. And again, the big thing, we're just looking, is this positive or negative? These are test values. And so the denominator is also definitely positive. So positive divided by positive, that indeed gives me positive. So now with this work right here, I can say, so x equals 2 minimizes distance. And so now I've answered the question, right, that I set off to answer, right, find an x value that actually minimizes distance, aka is closest, right, and I've shown all the necessary work to actually prove that it is a minimum. It's not just a critical point. We know it's a minimum. All right, and with that, let's go ahead and move on to our second optimization problem. We have this diagram below, right? We have a woman's currently starting at point A, is going to travel to point B. First she's going to swim, then she's going to walk. And the only thing that's really not in this picture is that, right, the distance from point A to point B, it's 10 miles downstream. So right here, here to here, this is 10 miles. The question is, which route would take least amount of time? So S is going to denote the variable in distance that she swims. W is going to denote the variable, the distance, right, that she will walk. And X is going to be the difference between the 10-mile downstream and the walking distance. All right, so a lot of things. Let's write down some equations. So first of all, right, X and W, if we add those together, those are going to give us 10. So let's see, X plus W is going to be equal to 10. And that's really kind of what this was saying right here, right? It's going to be, oops, not up there, the last couple lines. X is going to denote the difference between 10-mile downstream distance and the walking distance. And again, walking distance was W. A lot of these things are relating on distance equals rate times time. So that's kind of an old, maybe physics equation. Distance equals rate times time that we need here. And so, right, we have different types of distances, right? We have a swimming distance and we have a walking distance. So we could say the swimming distance is going to be equal to, and this is going to be her swimming rate times her swimming time. So we can use maybe little subscript notations to use swimming, right? And in fact, we see that she can swim at 3 miles per hour, right? So in fact, her rate is going to be 3 here. So, okay. We also have, so that's just the swimming stuff, walking. Walking, well again, walking distance is going to equal walking rate times walking time. So the rate at which she walks and the time that it takes her to walk that distance. Well, the rate at which she walks, right, she can walk at 5 miles per hour. So we're going to go ahead and replace this. Instead of walking rate, we're going to write 5. And our goal is to find T, right? T denotes the total number of hours that it would take the woman to swim and then walk all of these miles, right? And we want T as a function of only X. So, okay, T, the total time, this is going to be equal to, well, the swimming time plus the walking time. So the time that it takes her to swim plus the time that it takes her to walk. And so that tells me over here that I want to go ahead and rearrange these, right? I want to solve for T sub S, right? The swimming time. So T sub S is going to be equal to the swimming distance divided by 3. And the time that it takes her to walk, well, that's going to be equal to the walking distance, W, divided by 5. So let's go ahead and input these. So S divided by 3 and W divided by 5. And so we're getting someplace, but remember, we want this to be a function of only X. Only X. So that's where we need to start using maybe like this equation right here. So right, I have a W, I would like an X. So this tells me the exchange rate, right, between W's and X's. I could go ahead and write, well, W is equal to 10 minus X. So everywhere I see a W, right, I could go ahead and put a 10 minus X. Still, I have to divide by 5, and I have to figure out the swimming bit here. All right, so S, somehow I get, instead of S's, I want X's. So they sound close. So I go back and I look at my picture, and right, it kind of looks like I have a triangle here. Right? I have a way, though, that I can relate X and S, and that's going to be with the Pythagorean Theorem. So this would say that X squared plus 4 squared, that's 16, is equal to S squared. Oops, there we go. And so if I take the square root on both sides, remember this is a distance, so it's going to be positive, so I'm going to choose the positive square root. I get S is equal to the square root of X squared plus 16. So let's go ahead and input that. So the square root of X squared plus 16 divided by 3. And now I have my t, right, my total time that it takes to walk and swim, right, in terms of only x. So that's the big thing with these optimization questions is, right, trying to figure out what equation do you want to optimize. All right, so reading this second part, right, again, which value of x will give us the optimal route that minimizes time? Again, yes, we want to prove that we minimize time. So here we are, we have a function now that we can take the derivative of. Let's do that. T prime is going to be equal to, and so let's see, when I take the derivative of this, well, I have the square root, so the 1/2 comes down. We have x squared plus 16, reduce our power by 1, so that's going to go to negative 1/2. Now we multiply by the derivative of the inside, and that 1/3 is along for the ride. And then when I take the derivative of this right-hand side, let's see, the derivative of that negative x is going to be negative 1, and that one's divided by 5 here. Alright, so at this point we're trying to figure out when is this undefined and when is this equal to 0. Again, we're looking for critical points here. So let's go ahead and maybe with this negative exponent, with the square root and all that stuff, let's start maybe simplifying this down a little bit. We see there's some 2's here that would nicely cancel out. I'm going to go ahead and rewrite this as x. So right, we still have an x in the numerator. And then that negative exponent pushes this into the denominator. And the 1/2, right, that's going to make it the square root of x squared plus 16. And in fact, instead of writing plus here, let's just go ahead and write minus 1/5. So okay, now this is a little bit easier to look at. Let's see, is there any place where this would be undefined? So is there any place where I'm dividing by 0, or when I'm taking the square root of a negative, for instance? Well, the fact that this x squared plus 16, right, that's never going to be negative, right, because x squared is going to be positive, or at worst case 0, plus 16. So that's always going to be strictly positive. In fact, it's going to be 16 or larger, so I'm not going to get 0 there either. So really, it doesn't look like I'm ever going to divide by 0, and I'm never going to have a negative under the square root. So my only hope for critical points is when this is equal to 0. Remember, we get critical points when this is either undefined or equal to 0. So, okay, now let's go ahead and solve this. So I'm going to have 1/5 is equal to x divided by 3 square root of x squared plus 16. Let's go ahead and cross multiply. So I'm going to have 5x is equal to 3 square root of x squared plus 16. And now, let's see, I'm trying to solve for x here, so maybe I should square both sides, right? The square root is kind of annoying. So if I square both sides, I'm going to get 9, and squaring that square root perfectly goes away, and then this becomes 25x squared. So I have 9x squared plus, I don't know what this is. I'm just going to write it as 9 times 16 for the time being, 25x squared. And now let's go ahead and subtract. So if I have 25x squared and I subtract away 9x squared, well, that's going to give me 16x squared. And that was equal to 9 times 16. Oh, look, so I don't actually have to know what that is. Those 16s now perfectly cancel. And I just have x squared is equal to 9. So therefore, x is equal to either plus or minus 3. So let's go back here and see, does negative 3 really make sense? Well, no, it looks like our x value, right, our x value is from across point A and it goes this way, right? If it was negative 3, that'd be kind of back here. So we could specify even a domain for x, right? So x should be in the interval. Maybe the smallest value it can be is 0, and the largest value can be, well, it's 10 miles downstream, so it wouldn't make sense for it to be any larger than 10. So since the domain is between 0 and 10, right, we're only going to choose the positive square root, so just plus 3. So again, I only have one critical point, and again, it asks which value will give an optimal route, and so I hope that it's this one, right? But it's not guaranteed. I have to actually show that I've minimized the derivative. And so if I want to show that I've minimized the derivative, I need to pull out one of these, nice number lines here. And again, I'm going to be plotting stuff about t prime, and I'm hoping that 3 works out for me. So let's go ahead and maybe choose some test points here. So I'll choose maybe 2 and 4 are some natural test points. And again, I'm going to be plugging it into the derivative here. So t prime of 2. So that's going to be 2 divided by 3 times the square root of 2 squared. That would be 4 plus 16. That's going to be 20 minus 1/5. And the question is this positive or negative, right? We don't get calculators, and so we have to be a little bit good at, approximating these things. So I'm just going to go ahead and say approximately. And the only really kind of challenging thing is the square root of 20. Well, the square root of 20 is somewhere between the square root of 16, that's 4, and the square root of 25, that's 5. So it's somewhere between 4 and 5. And it seems to be kind of, in the middle-ish. So I'm going to go ahead and say that this is around 4.5. So we're going to have 2 divided by 3 times 4.5 minus 1/5. All right, so let's go ahead here. 3 times 4.5, well, that's going to be, let's see, 12, 13 halves. So 2 divided by 13 halves. Sorry, I mean 13.5. That's different. So 2 divided by 13.5 there. And then finally, let's go ahead and simplify this. We're going to have 1 divided by, and if I cut 13.5 in half, well, if you cut 13 in half, that's going to be 6.5. And if you cut a half in half, you get a quarter, right? So that's going to be 6.75. And you subtract away 1/5. And so if you really wanted to, you could get common denominators and whatnot, but hopefully we can agree, right, that 1 divided by 6.75 is smaller than 1/5, right? Just like a third is smaller than a half, or a fourth is smaller than a third, right? When you divide by more, you get a smaller number than if you divide by less, right? I would rather have half of a pizza rather than a third of a pizza. All right, so since this is a smaller number, subtract away a bigger number, this is going to be less than 0. Which is what we were hoping for, right? Again, we're hoping that 3 is a minimum, that this has minimized the time. And likewise, when I plug in 4 here, I'm really hoping that I get a maximum. Sorry, that I get a positive number. So let's go ahead and try this. So if I plug in 4, t prime of 4, again, and I'm going back to my derivative up here, which I have circled. So when I plug in 4, I'm going to have 4 divided by 3, and the square root of 16 plus 16, that's going to be the square root of 32, minus 1/5. Okay, so again, this one we're going to approximate here. I'm going to say the square root of 32 is around the square root of 36. The square root of 36 would be 6. So I'm going to have 4 divided by 3 times 6 minus 1/5. And so this is going to be close to, let's see, 6 times 3 is 18, so 4/18 minus 1/5. So, okay, this is approximately equal to, let's see, this would be 2/9, or that's going to be 4.5 divided by 1/5. So again, I have something right here, right? I divided by less, and I subtract away when I divide by more, right? So this is going to be a bigger number, subtract away a smaller number. This is going to be positive here. So this indeed does go decreasing and then increasing. The other way that you can do, and I've shown you kind of the more difficult of the two, just because if you go this route, it is possible, but you have to do this kind of estimations right here. The other way that you can do this problem is with the closed interval method, right? Because our domain is a nice closed interval. So back from 3.1, we learned about the closed interval method, and this says, well, that you would need to calculate out t of 0, t of 3, and t of 10. And whichever one of those is the smallest, that's going to be your absolute minimum. And in this case, we'd be able to see that t of 3 would be the absolute minimum. So either way, because you have the closed interval method, right, this one also works, but in general, the number line kind of works more often. So all this work shows here that x equals 3 minimizes the time taken, or the total time taken to cross the river and get back to camp. All right, decently long problem. Those optimization ones are.